Welcome to this explainer. Okay, today we're diving into one of the absolute most spectacular, violent, and honestly universe-altering events out there, the core collapse supernova. We're talking about the dramatic, catastrophic death of a massive star. And surprisingly, it's literally the very reason we are here today. So, let's just jump right in.
Just to set the stage, let's talk about scale, because destiny in the cosmos is all about mass. You've got stars like our sun, right? They live for billions of years, and they end their lives relatively quietly. They just kind of shed their outer layers and eventually fade out as a white dwarf. But massive stars, and we're talking stars packing more than 8 to 10 times the mass of our sun, they take a vastly different, far more explosive path.
And this brings us to a mind-bending question, which is really the central mystery of our explainer today. How does absolute stellar destruction, a catastrophic explosion that obliterates a star, actually create and distribute the building blocks of planets and even our own bodies? It's this incredible paradox where creation stems directly from absolute destruction.
Now, before we get too deep, we got to make a quick distinction. You might have heard of type A supernova. Those are thermonuclear runaway explosions that happens when a white dwarf basically steals too much matter from a companion star and completely blows itself up. But today, our focus is entirely on core collapse supernova. This is the catastrophic gravitational implosion of a massive, single star that simply runs out of gas.
Section 1. The battle against gravity. Think of a massive star's life as this epic, millions of years long tug-of-war. On one side, you have the relentless inward crush of gravity. On the other side, pushing back, is the outward pressure generated by nuclear fusion. So over millions of years, the star burns hydrogen into helium. When the hydrogen runs out, the core shrinks, it gets hotter, and starts fusing helium into carbon. This basically creates a nested onion skin structure inside the star of progressively heavier elements: carbon, neon, oxygen, and eventually silicon. And because heavier fuels yield less energy, each stage is faster and hotter than the last. That final silicon burning stage, it might literally only last a few weeks.
Section 2. The iron core crisis. Eventually, the star hits a literal cosmic brick wall. It's built up this dense core of iron. Now, iron is tricky. It has the highest binding energy per nucleon. What that means for the star is you cannot fuse iron to generate energy. Actually, doing so absorbs energy. So that outward thermal pressure we talked about, it completely shuts off. The core is now supported only by the quantum mechanical resistance of its electrons, something called electron degeneracy pressure. But there's a hard limit to this. When that inert iron core reaches about 1.4 solar masses, known as the Chandrasekhar limit, that quantum support catastrophically fails. Collapse is completely inevitable.
And this failure triggers what is basically a microscopic doom loop. As the core starts to squeeze, the intense heat creates these high-energy gamma rays that actually smash the iron nuclei back into helium and neutrons. It's a process called photodisintegration, and it acts like a massive thermal drain, just sucking energy out of the core. At the same time, electrons are being crushed right into protons to form neutrons and neutrinos. This is called electron capture, and it's terrible for the star because it's removing the very electrons that were supporting the core in the first place. With its support gone, the core goes into a literal free fall, collapsing inward at speeds up to 23% the speed of light.
Section 3. Implosion and the bounce.
This entire massive structural failure, the implosion of an Earth-sized stellar core, it all happens in mere fractions of a second. The core collapses inwards until it reaches nuclear saturation density. That is roughly 2.5 times 10 to the 14th grams per cubic centimeter. Let's put that incomprehensible number into perspective, because it's wild. Imagine cramming 200 million heavy trucks into the volume of a single gaming die. That is how densely packed the center of this dying star has become. At this insane density, the strong nuclear force becomes fiercely repulsive. The inner core suddenly becomes totally incompressible. It halts instantly. The outer layers of the core, which are still falling in at a fraction of the speed of light, slam into this hard proto-neutron sphere and violently rebound. This sudden halt creates a massive outward-moving pressure wave that immediately steepens into a supersonic shock wave. Astrophysicists call this event the bounce.
So the shockwave is tearing outward through the star, but then it stalls. As it pushes through all that infalling iron material, it loses an enormous amount of energy just tearing apart the remaining iron nuclei. After moving maybe just 100 to 200 kilometers, the shockwave stops. The star is dying, Matter is still raining down, but the explosion is paused. A failed supernova at this point would just collapse straight down into a black hole. So, what saves the supernova?
Section 4. The Neutrino Rescue Mission.
Enter the unexpected hero of our story, the most elusive, ghost-like particle in the universe, the neutrino. When that core collapses into a proto-neutron star, it releases a staggering amount of gravitational binding energy. And astonishingly, about 99% of this energy radiates away not as visible light, but as a colossal, hyperdense blast of neutrinos.
Now here's the absolute crucial point, the delayed neutrino heating mechanism. Even though neutrinos usually just pass right through normal matter without interacting at all, the matter right outside the newly formed neutron star is so incredibly dense that a tiny fraction of these neutrinos actually couple with the matter. They deposit their immense thermal energy in the region just behind that stalled shockwave. This intense neutrino heating effectively boils the material, reigniting the outward blast, pushing the shockwave forward again, and successfully blowing the entire star apart.
The total energy unleashed here is almost beyond human comprehension. Astrophysicists measure it in foes. That's 10 to the power of 51 ergs. A core collapse supernova releases about 100 foe of neutrino energy and 1 foe of kinetic energy. To compare, the most powerful thermonuclear bomb ever built on Earth yielded about 10 to the power of 24 ergs. A supernova is billions of times more powerful. It's the ultimate cosmic display of destruction.
Section 5. Remnants and Cosmic Legacy.
So, once the explosion clears, what gets sent out into the cosmos? First, let's look at what astronomers actually see from Earth. They classify these explosions observationally based on light spectra, which basically tells us what elemental layers the star managed to hold on to before its violent death. A Type 2 supernova shows strong signs of hydrogen. But if strong stellar winds or maybe a binary companion stripped away the star's outer layers before it died, we see something different. If it lost its hydrogen but kept its helium, it's a Type IB. If it lost both its hydrogen and helium layers, it's a Type IC. We call these stripped envelope supernova.
And what about that core that was left behind? Well, the final compact remnant heavily depends on the star's initial mass, its chemical makeup, its rotation, and its magnetic fields. If the explosion succeeds, we're usually left with a hyperdense neutron star. But if the star was exceptionally massive, or if that shockwave failed to revive and matter just kept falling back down, the sheer weight might crush the core completely out of existence, forming a black hole. Today, astronomers don't just use optical telescopes to look at the light from these explosions. Because of the deep internal physics, a core collapse supernova is what we call a multi-messenger event. We can detect the electromagnetic light of the expanding debris, sure, but we can also detect that initial burst of neutrinos that actually arrive even before the light does. And as the dense core churns and boils during the collapse, it produces ripples in spacetime itself, gravitational waves. By combining all three of these signals, we can peer directly into the heart of the explosion.
Which brings us to why this matters to you and me. The intense heat and pressure during the star's life, and especially during the explosive shockwave of the supernova itself, act as a massive cosmic forge. They create and distribute heavy elements throughout the galaxy. The oxygen we breathe, the calcium in our bones, and the iron in our blood were literally forged in the dying moments of massive stars. So, to wrap up this explainer, I'll leave you with this thought. If the very iron pumping through your veins right now was forged in the catastrophic, world-ending implosion of a massive star billions of years ago, what other cosmic mysteries are hidden in our own DNA? Thank you so much for exploring the epic deaths of stars with me today. Keep looking up and stay curious.